You can start up again. All right, now that we are definitely confirmed it's not our building, and it stopped anyway. All right, so to do any stoichiometry problem, general procedure, write a balanced chemical equation. It's always first and foremost. You know, I always say chemistry first, numbers second. Okay? Second thing, convert mass or molarity or atmospheres to moles. Because with stoichiometry, it's not just grams that you might be given. You might be given molarity, which you might remember from Chem 107. You might be given atmospheres that we're dealing with a gas. As we go through the semester, we'll do examples of stoichiometry with not only grams, but also molarity and atmospheres. Then you convert the moles of one substance into the moles of another substance using the stoichiometric ratio. Convert the moles of the new substance back into grams or molarity or atmospheres. Determine a percent yield if applicable. Now I have your little 2-star symbol for this. Footnote, if a limited reactant problem is at play, you have to determine which reactant is limiting before proceeding to step 3. Okay, so that's just a little footnote there. So here's a simple stoichiometry problem. It says, what is the percent yield, okay, of the reaction if 50.0 grams of lithium hydroxide with excess carbon dioxide produces 72.8 grams of lithium hydrogen carbonate, or lithium bicarbonate. So, here it gives us a reaction. Anytime you've got chemistry going on, you got to think about, okay, what kind of problem do I have? Do I have a limiting reactant problem, or do I not have a limiting reactant problem? So the way that you can tell is if I'm given only a mass of one product, if I'm given only a mass of one reactant, then I know it has to be just a regular simple stoichiometry problem. So I'm only given 50 grams of this. I'm not given any mass of this. And in fact, it tells me excess, which is always nice when it says excess, because it gives it away that we can assume at that point that we only have to worry about lithium hydroxide in order to figure out how much product is produced. And then it gives us another mass, but it gives us a mass of product that's produced. It's talking about percent yield, so what would this number maybe represent for percent yield? So the equation for percent yield is actual divided by theoretical yield times 100. So would that 72.8 grams, would that be an actual or percent yield, or actual or theoretical? It has to be an actual. Right? We weren't there when they did the experiments, so they had to tell us what was actually produced. So it's giving us a mass of this, it's giving us a mass of this that was actually produced. We have to calculate, in theory, how much of the product is produced based on the mass of the reactant that it gave us. Right? That's the idea here. Okay, so putting the actual yield aside for now, what do we do with that 50 grams? All right, we got 50 grams of LiOH. Hopefully this looks familiar to you, these kinds of problems.
You want to convert it to moles of lithium hydroxide?
Right, convert it to moles. Molar mass of lithium hydroxide, turns out it's about 24. My notes here just have one decimal place, so let's work with that. 24 grams of lithium hydroxide for every mole of lithium hydroxide. And now we have a mole ratio. What is it?
1 mole of lithium hydroxide gives you 1 mole of lithium bicarbonate.
Right, so 1 mole of lithium bicarb is produced for every 1 mole of lithium hydroxide. You're going to be inclined to not write the actual compound when you write out your units, but I encourage you to do that. Okay. Not just units, but identifier of the unit. The mole ratio might not be 1 to 1 sometimes. Maybe it's 3 to 1. Maybe it's 5 to 3. You know, it depends. And the last step. Yeah, molar mass of lithium bicarbonate now. So that works out to 68.0 grams of lithium bicarbonate for every 1 mole of that lithium bicarb. Here's one error that I sometimes see students make. What if this was a 2 over 1? Okay, what some people do is they say, oh yeah, well this was 2 over 1. That means I multiply the molar mass by 2 as well. All right, some people I've seen do that. Always remember molar mass is the mass always for 1 mole of substance, not for 2. So if you did multiply this by 2, you'd have to say, well, it's for every 2 moles at that point. Or you can just say, all right, stoichiometric mole ratio is 2 to 1. Well, that takes into account the coefficient change, right? So you work that out, it comes to be 142 grams. So is this our actual yield or theoretical yield? Right, this is the theoretical yield. So usually with these kinds of problems, we're always calculating how much we should produce in theory, but we know that a lot of chemical reactions are not 100% efficient. Not even Walter White in Breaking Bad could get 100% pure methamphetamine, right? So all reactions, even in Walter White's case. Okay. Didn't even remember what his percent yield was? It was 96%, right? The previous record, if you read online, was 92%. So he was 4% better. Which in reality probably isn't possible, but it's a TV show anyway. So all simple stoichiometry problems, starting with mass, all have a similar form to them. And if you've taken my Chem 107 class, you'll know the lame song I use. But for those of you who are new to me, here it goes. Okay, so do you know the singer Meghan Trainor? You ever heard the artist Meghan Trainor? And she did this song. And it goes something like, it's all about that bass, about that bass, about that bass. You know that song? Okay? So for simple stoichiometry problems that start with grams, it's all about them grams. Moles, moles, grams. Moles, moles, grams. Okay? And that's, a way to, sort of, I don't know, for simple stoichiometry, you can remember that form. Okay, so there, it's over now. So now we have this, so sometimes I'll call these Meghan Trainor problems just because, simple stoichiometry. Okay, so we have our theoretical yield. It's asking us what is the percent yield. So what do we do from here? Right, actual over theoretical. So percent yield is equal to actual over theoretical yield times 100. So our actual was what? Yeah, it gave us 72.8. In theory, theory, we should have produced 142. And punching that in gives us a percent yield of 51.3%. That's actually not too uncommon for a lot of chemical syntheses. I've heard a lot of other syntheses take a lot less than, or give a lot less than 51.3%. Some of them give 20% yield. So some products are just really difficult to synthesize. But so this combines a Megan Trainor's simple stoichiometry with percent yield. I figured that'd be a nice review problem to show. Okay. Any questions on Megan Trainor or simple stoichiometry problems? So this is if you're given one quantity, one amount of a reactant. But what if you're given two? Okay, what if you are given two masses, one of each reactant? Right, what happens then? And it gets a little more complicated at that point. So for any limiting reactant problem, it starts just like normal. Write a balanced chemical equation. Produce an amounts table of initial reactants. So I have here, produce an amounts table of initial reactant amounts in moles. So this is going to be different. Determine the limiting reactant by dividing the initial molar amounts by the reactant coefficients. And the smallest ratio gives you which one's limiting. Okay. Use the limiting reactant to determine the change in moles for all other reactants of interest or products. And then calculate final molar amounts. Convert the final molar amounts into mass, molecules, or whatever it is. Okay, so what is an amounts table? An amounts table is essentially a spreadsheet, like a Microsoft spreadsheet. We were doing it in some Excel last week. And so you've got a column for each reactant, each product, and you have a row, and you'll have three rows. Okay, you'll have initial row, change row, and then final row. I arbitrarily picked a really simple equation just to illustrate the amounts table. So this reaction involves hydrogen gas reacted with chlorine gas to give you 2 moles of hydrogen chloride gas. Initially, I just arbitrarily picked these amounts, but if you have 1 mole of hydrogen gas and 2 moles of chlorine gas, you would expect, not surprisingly, that the hydrogen runs out because the reaction is 1-to-1. So because the reaction is 1-to-1, the smallest amount that you're starting with ends up running out first. That's easy to see, but what if the coefficients aren't 1-to-1? And that's where it gets a little more, you got to pay attention more. Also notice that there's a 0 moles here for hydrogen chloride gas. Why do you think it's 0 for the initial amount? You don't have any to start with. You haven't done the reaction yet. So in the beginning, you don't have any product formed, so it's always going to be 0. So this is just for the first row, initial amounts. Then you can determine the change. Now if I divide 1 mole by a coefficient of 1 for hydrogen, what number do I get? 1 divided by 1 gives me 1. Okay, if I take 2 divided by 1 for chlorine, that gives me a number of 2. So which one is lower? The 1 from the hydrogen or the 2 from the chlorine? The 1 from the hydrogen is lower. So because I know this, it tells me that I ended with 0 for my final amount for hydrogen gas. I know it's going to run out. So 1 minus the 1 mole I'm losing equals 0. 2 moles of chlorine gas minus the 1 mole of hydrogen that I'm losing equals 1 left. 0 plus 2 gives me 2. Okay, why is this 2? Well, it's because I produce 2 moles of HCl for every 1 mole of hydrogen gas. So I'm producing double the moles of HCl for every mole of hydrogen gas that I'm using. This is the general structure of an amounts table. So we call H2 the limiting reactant, okay, and chlorine gas is the excess reactant. So there's some left over. The initial moles of both H2 and Cl2, again, just to repeat, I just picked these arbitrary amounts. So 1 mole for hydrogen, 2 moles starting amount for chlorine gas. I just pulled them out of thin air. I just said, okay, I'm just going to make up anything. If atoms can make up anything, I can make up everything. So, okay. Just FYI. Yeah, right. FYI, so for Chem 111B, second semester general chemistry, they call these ICE tables. Okay, so you will use these next semester. And so that's why I'm showing them to you now. Okay, so limiting reactant, just the concept of it. It's like going to Panda Express, and when the orange chicken runs out, the line stops. So for Panda Express, the orange chicken is the limiting reactant of Panda Express. That's my analogy for limiting reactant. For this equation, it's hydrogen gas. Okay. If you don't need a Panda Express, then forget I ever mentioned it. Here's a sample problem. All right. Try to do as much as we can. Last 10 minutes or so. So aluminum and oxygen react to form aluminum oxide. Clock's fast. In an experiment, 75 grams of aluminum and 200 grams of oxygen produce 125 grams of aluminum oxide. Okay, what is the theoretical yield in grams of aluminum oxide? B, what is the percent yield of aluminum oxide? And then C, how many grams of excess reactant are left over? So does anyone remember a problem like this from 107, Chem 107? Maybe, maybe not. Okay, so what I'm going to attempt to do, I'll probably not have time to do the 107 way. I'll show you how to do what most professors show in Chem 107, and then probably next time I'll show you how to do the amounts table way. All right, so Chem 107 solution. So we'll just do part A. What is the theoretical yield? Does anyone remember how to do limiting reactant from Chem 107? What might be the first thing we might want to do? Yeah, gotta get the chemistry down, right? That's first and foremost. Chemistry first. Okay, so it says aluminum and oxygen react to form aluminum oxide. So we have aluminum, oxygen. How do I know aluminum isn't like Al2? How do I know that? It's not one of the diatomic elements, right? So it's just aluminum, metal. All right, so aluminum, metal, oxygen gas. All right, and then aluminum oxide is my product. And then I got to balance it. So I can pick any element here. I'll start with aluminum. So if I do 2 aluminums, I got 2 here. I've got 3 oxygen. I got 2 here. It looks like I'm going to have to say 3 oxygen here and 2 oxygen there, so I have 6 O's on both sides, which means I now have to change the aluminum coefficient here to a 4. All right, so 4, 3, and 2. So from Chem 107, general strategy was take the grams of each reactant, convert them into moles of product, and see which one comes out smaller. Right, that's a general strategy. So 75.0 grams of aluminum. Okay, and molar mass of aluminum is 26.98. And then we have our mole ratio. We produce 2 moles of aluminum oxide for every 4 moles aluminum. Is everybody okay with where I got this ratio from? So this 2 comes from that, and this 4 is from that aluminum. Okay. So I run that calculation, and I have 1.389 moles of aluminum oxide. That 8 is the last sig figure. And then I do the same thing for oxygen. (200 grams of oxygen) divided by 16, excuse me, not 16. What should the number be?
32.
32. All right, so now I got to say 32 grams of O2 for every 1 mole of O2. What mole ratio do I use for that?
3 moles of oxygen gives me 2 moles of...
All right, so 3 moles of O gives me 2 moles of aluminum oxide. So it should give me 4.1666 moles of AlO2. And then we look at, say, okay, which one's smaller? So it looks like the aluminum gives us a smaller amount. So this is smaller. Limiting reactant is aluminum. Now, when I was talking about amounts tables, I said, well, if you want to figure out the limiting reactant, you take the initial moles and divide it by the coefficient of that particular reactant. We're doing the same thing here. Okay, convert grams to moles for aluminum, but then just divide it by 4, and do the same thing with oxygen, grams to moles divided by 3, and whichever gives you a smaller number tells you which one's limiting. And the reason why we don't have to multiply through by 2 is because it's 2 for both of them. All right, and it'll always be that case for any reactant that you're dealing with. What if you had 4 other reactants? What if you had a reaction that said, you know, aluminum plus oxygen plus sodium dichromate plus some other compound? How do you find the limiting reactant then? Do you go through this calculation for all 4 of them? Or do you just say, convert grams to moles for each of the 4, divide by the coefficient, and look at which one's smaller? Right? You don't have to do the last step here, multiplying through by 2, because you would do that for all of them at that point. So I'm just kind of painting some parallels here. You've been doing this all along in Chem 107, but it just is going to look different when we do the amounts table. So since aluminum turns out to be limiting, what do we do then? We know we're going to only be able to produce this many moles at that point. So we would say 1.389 moles of aluminum oxide is my amount of product that I can produce. All right, so I'm basically taking this moles now and saying, okay, what is going to be my actual yield? Molar mass of aluminum oxide turns out to be 101.96. And I get over 1 mole. Okay, and that would give me 142 grams of aluminum oxide. So this is our theoretical yield. It's what we should produce. it tells us in the problem that 125 grams of aluminum oxide are produced. So percent yield equals some number divided by 142 grams. 125 is what it gives us. So we have 88% yield. All right, so I think we'll just have to end it here because we're getting close to